In this lesson, we're going to be looking at a quick overview of the life cycle of stars. So the star beginnings. So basically we start with a nebula, which is a massive cloud of interstellar gas and dust. And this is basically the beginning of a star. And it consists primarily of hydrogen and helium. So those are the two kind of main gases that you would find in the nebula. And we can kind of see examples here of three different nebulas that astronomers and scientists have been able to view. We have the Witch Head Nebula, the Crab Nebula, and the Orion Nebula. So you can almost kind of see how they have a kind of gaseous appearance to them, even though they are in space. So the next step, so once we have our nebula, the next step is a protostar, which is a massive concentration of gas and dust. So basically these gases and dust are kind of concentrating, and they eventually develop into a star after the nebula collapses. So we can kind of see an example here. You kind of see those gases getting close together in the one image on your right with the arrow. That arrow is pointing at a protostar. So you can kind of see how they are. And again, these are all viewed through telescopes that are very far from Earth. If you think of a star and you think of the sun is a very large star, all this is happening very far away from Earth. So it is hard to kind of see what they look like. Nuclear fusion. So once a protostar reaches a critical temperature of 1.5 times 10 to the power of 7 degrees Celsius, so that's 1.5, and then you're multiplying that by 10 with 7 zeros after it, nuclear fusion begins. So the hydrogen atoms fuse to form helium atoms, and they produce enormous amounts of energy. Right? If we think back to chemistry, we know that hydrogen is a very reactive substance or element, so you can think of the amount of energy that it's going to produce. And we can kind of see again examples in space of just kind of what they believe is nuclear fusion occurring. And then finally, a new star inside the nebula starts to emit radiation or energy. Energy from the core goes to the surface, causing the gas surrounding the star's core to glow. So again, we can kind of see that glow from Earth or from the sun. We see it glowing, it's bright during the day. We can also see the stars glowing at night, even though they're far away. And then the star eventually stabilizes at a particular size. So not all stars are going to be the same. You may have some larger, some smaller, but they're going to stabilize at a certain size. And if you think about the sun, it took about 30 million years, they believe, to condense and then finally begin to glow. So it's not like this is an instantaneous thing. It's like a snap of your fingers and then this happens. It does take a lot of time. So the Hertzsprung-Russell diagram. So what that is, it's basically the diagram you see to the right. And it's kind of a combination of different variables in a graph form. And it's used to classify stars based on their luminosity, spectral type, color, temperature, and evolutionary stage. So we can kind of see all the different types here, your blue giants, your red supergiants, your red giants, and your white dwarfs. We see the temperature and luminosity. There are other scales, but this is just a simplified version of it. But again, it's used to classify stars. And basically, again, we talked about this a little bit in the characteristics lesson, but the more luminous stars or the brighter stars are larger. So we can see kind of the luminosity scale on your vertical axis. The larger ones are brighter. Moving into death of stars, there are basically two kind of pathways that it could take depending on the size of the star. So if you have a star similar in size to, say, our sun, it goes through the following death. So basically, I was going to go through it. So the sun-like star, this is the longest, most stable period of a star's life. It converts hydrogen to helium in its core, generating heat and light. So again, that's its life. It's producing heat, generating light. And then it becomes a red giant. So as the nuclear fuel becomes depleted, the core contracts and the outer layers expand. So it gets larger. then becomes a planetary nebula. So now the outer layers of the star start to drift off into space. The star loses most of its mass to the nebula. So again, you think about the nebula was just a collection of gas. So this gas is, or the outer layers of the star are kind of drifting off. So those gases are drifting off and it's forming kind of a nebula. Next, we come to a white dwarf. So the star cools and shrinks, and it would eventually be only a few thousand miles in diameter. No nuclear reactions take place, and the faint star radiates its heat into space. So it goes from this red giant, it loses most of its mass to the nebula and becomes a white dwarf. Eventually, the star loses all its heat to space, and basically it just becomes a black dwarf, so it's just cold and dark. And that's the death of a star. So that's what scientists expect to happen to our sun. But don't worry, they don't expect this to happen for millions of years, I believe. So again, we have our red giant. So this is when the nuclear or hydrogen fusion restarts in the outer layer and it starts to expand and cool. So you get a red giant. White dwarf, you can kind of see an image here. So as the red giant ages, it sends gas and dust into space. So again, it loses it to the nebula. It loses mass until a hot, dim core remains. So the white dwarf is basically the core. And then it goes into the black dwarf. The other pathway for death that it could come across is if you have a giant star. So this is something larger than our sun. And so again, during its life, this is the longest, most stable period of a star's life. Again, it converts hydrogen to helium in its core, generating heat and light. So the life of a star is the same regardless of what size. What happens then after is becomes a red supergiant. So as the nuclear fuel becomes depleted, the core contracts and the outer layers expand. So again, same idea as in the past one, except now it's larger because we're starting with a larger star. Next comes a supernova. And so basically what happens is the core collapses in an instant. And the repulsive electrical forces between particles in the core overcome the gravitational forces, causing a massive short-lived explosion which blows away the star's outer layers. So basically, instead of it losing mass to the nebula and forming a white dwarf, basically the core collapses in on itself. It gets too big, it collapses, and it creates this massive quick explosion. After the supernova, we have a black hole, and I'm sure you've heard of a black hole before. I believe last year scientists were able to get the first image of a black hole. You might have seen it. It's like a orangey image, which looks like a circle. You've seen it probably in movies or TV shows. But basically, in the black hole, it contracts tremendously. All these outer layers, this explosion, it contracts and becomes a black hole. And it is incredibly dense with a gravitational field so strong that even light cannot escape. So that's where the black hole comes from. The gravitational or the gravity is so strong that light can't escape it. So if you think of on Earth, the gravitational field or gravity on Earth is so strong that we can't break through it on our own. We need to use planes, we need to use rockets, whatever it may be. We can jump, but then gravity pulls us straight down. Now imagine that it's so strong that anything we see can't exist because light can't exist. It can't escape it. If it's like trying to shine a light at something and you just see black. There's nothing, light can't escape it. That's how strong it is. So just another example of a supernova. Again, it's when the outer layers of a star explode outward. You get a large nebula of gas and dust, and it releases lots of energy, causing many fusion reactions. So supernovas tend to be how elements are formed. And this goes back to the Big Bang Theory as well. Neutron stars, again, these are cores that are left over behind after a supernova. So these would be similar to the white dwarfs in smaller stars. They're extremely dense and they're made up of tightly packed neutrons. And they may be tiny, but they have a large mass and 300,000 times the gravity of Earth. So you can already see we're kind of beginning to get towards that black hole category because there's so much gravity on these stars. And they spin very quickly, and these emit radio waves, which we can then detect as pulses. So we can detect neutron stars by listening for these pulses. And again, finally, we have black holes. So the core left behind from a collapsed star with an initial mass larger than 30 solar mass units. So again, these stars are larger than our sun. And the black hole is the result of the core that's left behind from these collapsed stars. So it's extremely dense quantity of matter, and no light or matter can escape it because of the gravitational pull or the gravitational field. It's so strong that light can't escape it. Yeah, and again, gravity is so strong that it pulls in all nearby matter. So essentially, it's pulling in all the matter around it. So just a quick summary. We have our stellar nebula, so a nebula that creates these stars, and then they go into either a average star, so kind of something like our sun, or a massive star, which is quite larger. From there, it goes into a red giant or a red supergiant. This is kind of when it's on its starting onto its death cycle, or its pathway to death, you could say. The red giant goes into the planetary nebula and then to the white dwarf. The red supergiant goes into a supernova, and the result is either a neutron star or a black hole. So again, just a quick summary of the life cycle of a star. You don't have to worry about our sun reaching that at any point, because it's currently still in its life cycle where it's emitting heat and energy, or using nuclear fusion to do that. So you don't have to worry about any of like the supernova or the explosion or the nebula occurring anytime soon.